Sublimation. So sublimation is the transition from a solid directly to a gas without melting in between. This can happen. The opposite of sublimation is called deposition, and that's going from a gas directly into a solid. So here we have an illustration of a block of ice, and these water molecules have thermal energy. They are vibrating, but they are fixed in place relative to each other. They can't move around, but they can wiggle in their seat, right? Some of these will have higher energy, and others will have lower energy. The average is related to the temperature. So you can have molecules on the surface that have enough thermal energy that they can actually break free from the surface. And a single molecule breaking free will be in the gas state. So that's what happens in sublimation. Particles, the highest energy particles in the substance, can break away and go directly into the gas states. So solids can also have a vapor pressure. Most solids, though, their vapor pressure is so low it's not worth talking about. There are only a few solids that we see sublimation like this in a significant way. So sublimation will usually happen at a greater rate in an open container. And this explains some things that happen in your kitchen. If you leave ice cubes in the freezer for a long, long time, they slowly get smaller. Ever find some ice cubes in the back and they're like a lot smaller than the rest of the ice cubes? Yeah, they didn't go on a diet. They sublimated. Okay. We experience ice crystals growing inside airtight bags of frozen foods. So it's a little disappointing when you dig out that bag of tater tots and you open it up and you dump it on the pan and there's like snow. Like, what the heck? I know I left it in there a long time. I just found it. Why is there snow in my bag of tater tots? Well, that's because water from the tater tots, the potatoes have water in them, water from the food sublimates. But in a closed container, it can't really go anywhere. So it will solidify or deposit itself again. And that's what makes the ice crystals. So all that moisture used to be in your tater tots. This is the same thing that happens when foods get, they call it freezer burn, but they become dehydrated. They've lost moisture. That's because the water sublimated out of them. This is also partly why your freezer gets a lot of frost buildup. The biggest effect, though, is when you open the door and you let warm air in. That brings in a lot more moisture. So you can get around some of these problems by using a deep freeze that is colder than usual freezer, or by sealing the food in such a way that there's no airspace. So then if the water begins to sublimate, it can't go anywhere, and so it just has to stay there. Any questions? So dry ice is actually solid carbon dioxide. And the reason it's called dry ice instead of, I guess, regular ice would be wet ice. What happens when ice melts? It makes a liquid. It makes water. It gets everything wet. Your sandwiches get soggy, right? Dry ice doesn't do that. It doesn't melt. It slowly goes away, but it doesn't melt. And so things that are stored in dry ice will remain dry. It sublimes at room temperature. Fusion. So fusion is another word for melting. So fusion and melting, and we do need to remember that fusion means melting because we're going to talk about the heat of fusion. And so what I think about is putting a bunch of chocolate chips in a saucepan and heating them up, right? And as the chocolate chips warm up and melt, they fuse together into one big piece of chocolate, right? So fusing and melting are the same thing. So if you increase the temperature of the block of ice, the molecules are going to vibrate faster, and at some point, at the melting point, they're going to have enough thermal energy to partially break from those intermolecular forces. They're not going to burst out into the gas state, but they're going to start sliding around, okay, and become a liquid. So melting is solid to liquid, freezing is liquid to solid. And you definitely should know what these terms mean, right? There was two more back here, sublimation and deposition, melting and fusing and freezing. So if we look at this heating curve, and here we're down below zero and we're looking at water, as you heat the ice becomes warmer. When it starts to melt, we see a plateau on this graph, just like we did when the water began to boil. Because as heat is put in, all of the heat goes towards the melting process, and none of it is used to increase the average thermal energy. So the temperature doesn't increase until all of the ice has melted. And so this can be helpful if you're, trying to cool stuff down. If you have water with ice floating in it and it's, been there a little bit and it's equilibrated, that water's going to be really close to 0 degrees Celsius. And putting more ice in it isn't going to make it any colder. But it's, going to stay that temperature pretty much until all the ice melts. Once all the ice melts, then you can increase the temperature of the liquid. And what we learned last week is you increase that up to the boiling point, and again, the temperature becomes flat until the transition of liquid to gas is finished. So we talked about the heat of vaporization, right? Here we're going to talk about the heat of fusion. So remember, fusion is melting. Melting is an endothermic process. You think about, well, how could I make this thing melt faster? I could heat it up, right? I could put heat into it. It's going to make that happen better. It's an endothermic process. So how we define the heat of fusion is the heat required to melt 1 mole of a solid. So here we have solid water going to liquid water, and this heat of fusion will always be positive. So melting is endothermic, that means freezing is exothermic. So if you freeze a mole of water, then 6.02 kilojoules per mole of energy are released into the surroundings. And this one is a little hard to get your mind around. But how do we freeze water into ice? Put it in the freezer, right? What does the freezer do? The freezer is pulling heat out of the inside of that box. There's a motor and a compressor and all that stuff under there. It's pulling heat out of the box. Drops the temperature. The water freezes. Now, I live in Reedley, which is, fruit country. And coming up on this time of the year, the citrus crop can be in danger of freezing. Gets down to like 26 degrees for several hours, and the oranges will freeze, and the whole crop's ruined, and it's really bad, really bad. So, you can't go out there and put blankets on the oranges. But one thing that does help is to water the fields. So they'll flood irrigate the fields, get the fields really, really wet. Because what happens is as the water freezes, it releases heat, which prevents the temperature from going down anymore. So when we look at this heating curve here, so if we're going backwards, The temperature's dropping, there's liquid water. It's not going to go below 0 degrees Celsius until all of the water has melted. And so that heat goes out into the air, and then they turn the fans on and help blow it around, and they can usually keep the oranges from freezing. Does anybody have any questions about that? I bet you most farmers couldn't explain why that works. So heats of fusion are generally much less than heats of vaporization, because when you melt the substance, the particles don't have to break away completely. They just have to break enough that they can slide around. So you're not completely breaking all the forces, and so less energy is required. So here's comparing heat of vaporization, going into a gas, versus heat of fusion, melting. And we see for these different substances, the heat of vaporization is much higher than the heat of fusion. Heats of fusion are also not something you would memorize. You would be given those on an exam or look them up in a table.